actually want to talk a little bit about like a new field. So people are starting to use neural networks or deep learning to model semiconductor devices. But I think so I first want to introduce a little bit about like what is a semiconductor device, like how it works. So I hope it will be more easy for everyone to understand. So so a semiconductor device is simply like it's merely a device that we can control how much current there are in the device, so that you can pass and process signals. So that's you can imagine the semiconductor device as a channel of river. And the current is like, imagine that you are controlling how much water is inflow in this channel. And there are several parameters of semiconductors. And one of those key parameters are the source voltage, which means like that's basically how much water you coming. That's kind of like how much you push your water from the beginning. And there's a drain, that's the end of the channel. That's kind of like you are kind of like drawing currents to the drain. And there's also a gate that's kind of like controlling how much currents there are, kind of like the depths of the water, something like that. It's kind of like controlling how much water you can get. And there's also some other parameters like the channel length, that is kind of like how long your channel is. So imagine that you are pushing an amount of water through the channel. Obviously, the longer the channel, it will be kind of like you are expecting lower currents, right? So it kind of like you input the same amount of water at the beginning each time, but the longer your channel, yeah, something like that. Didn't have a good analogy. Yeah, but the longer it's kind of like the channel length is something like the longer your channel, the more likely you have frictions during the water flow. So the length of the channel also affects, and there are also something like the channel wide is kind of like how wide your channel is. Yeah. So basically, in summary, is that there are several parameters that controls how your semiconductor device perform. And I think what's challenging is that these parameters actually take different levels of effects on the current. So source and drain. So the parameters like source voltage and drain voltage, they usually affects the how much current you get in kind of like with a magnitude of 10 or 20. Yes, Roger?
I was going to ask, so when we're talking about the parameters, are you including things like the dielectric thickness, the doping level, things like that? Or is it just the voltage, the gate voltage?
I think that's actually worth investigating, but currently I think the research has just been done on, yeah, that's mostly the current. I think the research is still stuck in voltage, source voltage, drain voltage, and something like that. For doping levels, I do see some. So I think some researchers has begun to study the ferroelectric devices, and they're trying to incorporate that in. But I think right now they are still in the beginning. Yeah.
Okay. Yeah. Thank you.
So yeah, so I do see someone that they simulate. So here's actually. So if I share my entire screen, so I do find one article. So this one, they study the ferroelectric transistors, and what they do is that they are assuming that the when you it's going to be kind of like defects in your substrates. That's actually kind of like things about that. You have like different distributions of drugs in your different distributions of rocks in your channel, then their distribution is actually going to affect your channel behavior, right? So what they do is that they use TCAD, which is semiconductors simulating software. So, and they input random morphologies of your channel. So, and the reason they use neural network is that they are hoping this will they're hoping that this will save them some time, because it usually takes a long time to run the TCAD. So I think that would that interest you, Roger?
Yeah, that's fine. Thank you.
Yeah. So yeah, so that's kind of like what they designed everything. That's just like put device models in the TCAD and use neural network to train and evaluate everything. Yeah. So I think I want to begin, but I think what I want to talk about today is like the development of kind of like some simple but like most important parameters like source and drain voltage. Yeah. So the challenge is that, so here's how the gate voltage affects the current IDS. The current is usually the output that in most semiconductor devices. So so the challenge is that so you see that VGS, the gate voltage, affects the output current in it's kind of like an exponential effect. But at the same time, VDS, it just kind of like affects the IDS usually by like 2 times. Usually this is less than 10 times. So I think that is one of the challenges in setting up like deep learning for semiconductor devices, because obviously these two inputs have a different level of effect on your device. So to see that this look at here, like for VGS, it affects the current from 10 to the minus 4 to 10 to the 10 to the 0 is kind of like this is 10,000 times, but VDS usually this is a very small effect. So I do think that's one of the challenges. So what is presented here is an early work. Yeah. So what is presented here is kind of like an early work. They try to process this, they try to solve this problem. So what they do is that they took logarithm of the IDS. So yeah, so they just took logarithm of the IDS, which is the drain current, and they just set up a simple neural network to solve everything. So I think what the parameter they use, this one is 8, this one is 3 or 4, I think. Yeah. So that's the way they want to solve it, and they do argue that they argue that you could actually, I think I'll bring back this one. So they do argue that like when you do the prediction, they're saying that like there are kind of like A neurons, B neurons, and C neurons in this network, and they are arguing that each neuron is actually more trying to model different parts of your devices, such that it may have a neuron that is mostly affecting this part, which is kind of like a big translating part, and there are neurons that is predicting the lower ones. I think why they argue that is probably that for example, if you look at the tangent edge function, so one of the typical functions, you will see that like some part of it change rapidly and some of it some of in some areas, tangent edge change rapidly, and in some areas it changes slowly, right? Yeah. So I think, but if you like, if you move it by some degrees, like if you move it left or right, which is I think the voltage, the W and D adjusting, you are actually able to, if you have like multiple tagging edge and one is monitoring, one is here monitoring some part, and the other is on somewhere else monitoring other part, I think this actually makes sense. Because we may kind of like have different tunings. Yeah.
Sholin,
Yes.
a quick question or half question, half comment.
Yeah.
So you said that this is one of the early efforts,
Yes.
and
Yeah.
so it said 2017. So I think in 2017, knowing what we know, it's not surprising that people built a relatively small neural network, but that maybe today we would build something bigger because we have more compute, we have GPUs and things like that.
Yeah.
Is that kind of where you're going, the direction you're headed?
Actually, no.
Okay.
I
All right,
haven't
just curious.
seen. Yeah, I think I opened the wrong. Oh yeah, no, I didn't open the wrong one. So we hope probably I was wondering, but I was thinking of the same question. But actually, the most I think the trend, rather than building up big models, the trend is actually going to incorporate more parameters. So,
Okay.
like for the early, yeah, I think that is why I said that this field doesn't seem to be very much developed. So in this early work, they only incorporate 2 parameters as the input. And the most recent one I've seen is published last year and this year. They are the same group, so they use the same kind of structure. So this is kind of like their structure. So in this work, I think they also try to incorporate. Let me see how much things incorporated in. Yeah, he's trying to incorporate. Yes.
Oh, sorry. When you said not bigger models, but more parameters.
Yeah,
do you mean more kind of raw physics parameters?
Yes.
Okay.
They try to put like more physical parameters, like
Gotcha.
yeah. So like this one, they include the channel length, channel height. It's kind of like
more inputs, kind of.
Yeah.
More input dimensions. Yeah.
Yes, it's kind of like they put more input dimensions of the shape of your channel. So, yeah.
Hey, Sholin, could you go back to that one graph? I'm trying to understand the slide 4, I believe it was slide 4.
Okay.
Yeah, on the yeah, there. What are we looking at on the XY axes of this thing?
XY axis of this one?
Yeah, I guess it's the same for both of those graphs, right? I'm looking at the units and I don't understand what it's saying.
Okay. They are of like a different axis. So the first one is VG. It's the voltage on here. The voltage on here.
Oh, okay. On the gate itself, then, yeah. Okay.
Yeah. And second one is VDS, is the difference between the voltage of here and here.
Oh, okay. Okay. All right.
That's why you can see the effect of these 2 parameters is actually huge difference. There's a huge difference in their effects. So VGS affect the current by like 10,000 times.
Yeah.
Like with from 0 to 1, but VDS affects it only from like 0 to 0.6.
Okay.
So kind of
okay.
6
Cool.
times. This one 6 times. So VDS 6 times, and the VGS is kind of like 10,000 times. So that's what I think is it's actually hard for you to build up this one. So I do think of something like if you use like because the neural network always come with some kind of like some yeah, so neural network is kind of like approximation. They always come with some error. But if you only use logarithm for the IDS, yeah, not sure if whether it will cause it may have some tendency to, or if there is some possibilities that you may have larger errors when you use logarithm to treat all the IDS. But so far, so I do a comparison that yeah, with the difference from so 0.9 and 0.8, their logarithm difference is around 0.1, but 0.2 and 0.18 is also kind of like around 0.1. So something I'm worrying about, but frankly speaking, I haven't thought of a good way to solve this. Yeah, I'm building up a model, but well, I'm able to kind of like simulate this one, but I do agree that if you do not take logarithm of your IPS, it's very hard. So I even incorporate like exponentials in my neural network, that if you do not use logarithm of the IPS, you can never, like your training is always kind of like stuck here. It cannot go deeper.
Okay.
It's very hard. So yeah, I was trying to kind of solve the problem through like the structures of neural network, but yeah, but probably that doesn't go well. So
I was just surprised that the neural networks being used are that simple as the scaling. You know, that kind of stuck out to me. That's the y-axis scaling. That, you know, you had such a large difference there.
yeah.
I was just thinking, you know, maybe the simplicity would cause some issues or something like that. Okay.
Yeah. So
by the way, as a side comment, I've tried doing some regressions where we predict the log of the target variable and run into the same issues. So if you think about it, right, if you add a fixed constant, the same error, to the log of something, that's the same thing as multiplying it by whatever, right?
Yeah.
So if you're multiplying by 1.1, then on a smaller number, that's going to be a small error. But on a large number, multiplying by 1.1 is a larger error. And so we were predicting things that were sort of like on the scale of 1 over x for integers. So not nearly as large a range as you're saying, like 10 to the 4th, right? I was just looking at sort of the difference, maybe like 30 or something like that, right? So like 1/2, 1/3, 1/4, 1/30th, right? So it was only really, a whatever, a 10 times, 20 times, 30 times difference between the smallest and the biggest values. But when we did the log, the prediction on the log looked pretty good. And then when we exponentiated it back into the raw target variable, then it was yuck. It was not good. So
I actually did that experiment before. So I do it with like a curve fitting. The log looks perfectly, but when I turn it back, ouch.
Yeah.
So I think especially if you have more parameters. Yeah, but one thing important is that actually, well, neural network, I think it does have a very good like it does have like a very good resistivity to kind of like noises. So yeah, and I'm thinking that one of the I think that I can think of two advantages of using neural network for semiconductor design modeling. So actually the area of semiconductor modeling has been going on for at least 30 years. But the process is very hard. It's actually very hard to build up models for this. The first issue is that like usually models are built up for devices with like new structure or most likely new material. When you are building a model, usually many times we still didn't understand the physics very well, and it is hard. it is kind of very costly to build up like experiments, and what's more difficult is that there are so many things in your devices, and even like a drop of dust on your device is going to kill everything. So this is a very sensitive one, and with lots of parameters, with lots of physics going on, it's actually hard to build kind of like a physics model. It usually kind of like takes decades to build up a good model. So that's why I think neural network will be actually be very useful. But so far what I've seen is that most research are done on simulated data. I hope I can talk about it in later, but whatever, just look at, let's still look at the structures. So I think I want to skip the second one because that's kind of like a little bit away from the first one. This one is using neural evolution. I think I want to put that later on. That's the only one I see that's kind of like discussing what structure we should use for the transistor modeling. So I think I want to jump to the third one. Yeah, so I think they incorporate like two important things in. So first is that they redesigned the loss function. So the first one we see, they didn't. I think they only use the MSE, the L2 loss as the loss function. But this one, they added something in. They also added the error of kind of like of the gradient of the curves. So the reason they do that is because the gradient actually matters. So the gradient of RDS to the VGS, which is the gate voltage, you see those one who changes magnitude of 10,000. So the gradient of the current to the gate voltage is actually called the transconductance, and that is of kind of like, that is of very important. That is of great importance if you want to use your channel. But what they find is that am I sharing this one? Let me double check. Am I sharing this one? Share screen. Yes. So that is so this is their article. Yeah. I think they find somewhere that okay, I don't know where to find it. I think they find something that like if you just use MSE to simulate everything, or is it this one? Wait, this is oh yeah, it's using something that some later people discuss, but they are the same. So the issue is that if you do not optimize your loss function, you may kind of like have something that it seems that it models pretty well, but when you look at it closely, it's actually yeah. But when you look at it closely, it's kind of like actually have some curves. There's lots of deviations, and this is something you don't want when you have your model. First, this doesn't make physical sense, and second is that this deviation is actually gonna cause a big problem when you are dealing with your device. So I think both this article that's the so yeah. So that's what the article stand for. Yeah. So that is what these two articles are trying to solve. So they actually do something on your loss function. Yes, Ted?
Thanks. So my question is, so I see they added a term for the gradient. Are they calculating that gradient based on the predictions of the model, Or are they calculating the gradient because the model's actually outputting something, a second value?
So I'm sure about, so I do know the process of this one. What they do is that when you input, so they do have a list of your GDS, of your derivative with your V. So that is something the simulated software, this is part of their data resource. So that's kind of like in their data resource, they not only have the IDS, the current and the VDS, the drain current and the gate voltage something, they also have the derivative as one of their inputs. So that is why they can calculate. Yeah, that is why they can calculate the how much it changes. So they already know this before. Already know this, and then they calculate what the derivative is from their model and use it as part of their loss function.
Okay, so it sounds like maybe they're making two predictions.
I think for this one, let me double check.
Yeah, I'm just curious because if you did this in a very simplistic way, okay, for any set of inputs, if I'm predicting the current, I simply get 1 point value. I don't know what the slope is there. I would have to like perturb my inputs in order to figure out the slope.
Yeah,
you see what I'm saying?
Yeah, but you see the VDS is already changing. So I think what they do is that they have this list and they are calculating the derivative at like each interval of your VDS. Like if you take two.
So Sholin, if you go, sorry to interject, if you, maybe it is there as the input in your previous picture, in your slide. Don't you have
this one?
In the slide? Yeah, this one right there. So right there, yeah, on the left. So do you have in the derivative going as the what you have at the bottom? This is the physics-based model.
Yes. Yeah. The physics-based model is a simulated software called BSIM.
And is that going as part of the input for your loss calculation?
I think this BSIM, yes, it can produce your derivatives. So yeah, this BSIM not only produce your current with different variables, it also produces derivative GM. So that's why they can get the GMs. Yeah. Does that answer your question, Deb? Basically, this is their data resource. Is that okay? Can I go on? Okay. Yep. So their biggest input. So first they updated their loss function, and there's the second thing is that I think this is something that's worth discussing, is that there's something called the Gumo test in the also the Gumo symmetry test in the semiconductor. The reason is that what they are saying that if your channel is symmetric, which means that if you look at it from left to right and look at it from right to left, it's the same structure. Then also like if this is a kind of like a symmetry structure, it's like then if you flip the voltage, if you flip the position of your source to gate, it should actually give you the same output. Yes, Giants?
Yes, so I have a couple of questions. One is, how is this used? Like once you predict the current, how do they use that? Like where is it applied?
I can show I can show a simple One of it. Yeah, here. Okay. So where it can apply is how your computer can compute everything. So or maybe I can just use this graph. Yeah. So basically, this is too blurry. Yeah. Not this one. Do I have a better one?
So I guess you're trying to show there's a circuit with like a few transistors, and then you want to model the current for each of them.
Yeah.
And okay, I see.
And this is actually the key part of your computer. This is how your computer can give you, can let you browse the website, can give you answers, can give you like what is 1 + 1. Yeah. So
And do they assume that all of the transistors, let's say in this diagram, circuit diagram, do they assume that all of them are modeled similarly, or do they have some variability in terms of this gate could act one way and this G2 could act a different way and so on?
how to say, these are kind of like, these are different channels. These are different kind of like water channels, and you basically just connect your water channels into a system. And
Okay.
usually the Q1, Q2, we do not assume all the channels to be kind of like perform exactly the same. So you have models for each of them. Yeah, although in this one, yeah.
Based on the voltage that they get. Is
Yes,
it?
but
Okay.
not only based on the voltage, but how they react to the parameters, like how they react to the voltage, is usually different.
I see. And in the semiconductor industry, they talk about gate level simulation. Is this in any way related to that?
Yes.
I see. And so is this somewhat, and the benefit of doing it this way using neural networks, is it because it's faster or something, or what's the motivation?
I think it's because it is faster.
Okay, I see. Okay, cool, thanks. And the other question I have is, the curves that you showed, of the current, has that been modeled mathematically, as a function of VGS and VDS?
How to say, it can be modeled mathematically, but your mathematical model will usually produce something that is kind of like fitting the reality, but it has deviations. Like it's very hard to produce a model mathematically to predict every condition in your device. Yeah, there are, like, usually we can usually see that VGS is kind of like you can say like IDS is like in something to the E to the VGS something. But first, usually the develop of this physical model is very hard, because you see, you have like a you have the level go up and down, and you have a current flow in. There might be and how do you model kind of like the inflow of current with the changing of your water level, with the change of your high level water. Yeah.
So for the ones that you have shown so far, they just use the two voltages, VDS, VGS.
Yeah, that's the simple one.
So I guess later on, do they start using all the other things that you just talked about in their model?
Yes,
I see.
Yeah, this one they just try to incorporate more in. I think that's in the fifth one.
Yeah, we can wait for that, but okay. I think I got my answer. Thank you.
Yeah, that's kind of like the most recent part. Yeah, so there so for because Yeah, I think I'll be better to choose slides. So article number 4 and article number 5, well, they are basically of the same group. So 5 just uses the structure of number 4. Yeah, so like here, they just like incorporate this epsilon to kind of like to show like what's the difference between log IDS and the to the VGS, I think something like that. Yeah. So they're trying to use this epsilon to correct the small error if you just use like IDS equals to log IDS equals to VGS blah 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 something. Yeah. So that's why it covers physics-based modeling.
Okay. Okay. Thanks.
Yeah. I hope it makes sense.
Yeah, it
So,
does. Thanks.
yeah. And I think what 5 output in here is that they also incorporate that they rather not only use the first derivative, they also incorporate the second derivative in. So basically that's what they do. That they, yeah, this is basically one thing that they shows that okay, they can simulate different terms. Yeah. This is just to show that okay, they can it can not only so for these graphs, their input data is so not all does. So the neural network does produce something that to predict the device. Yeah. So like it can predict situations that that was not using as the input. Yes, so that's kind of like some test part. Yeah. And another thing is that it can predict something that is hard to develop a physics model. So if you have some physical phenomenon that is hard to understand, or say it's too complicated to build a mathematical model, well, you can use neural network to build it up. So basically, that's what they are talking about. Yeah, that's what they are talking about here. So usually this phenomenon is actually it's hard to predict with like purely mathematical derivation, but with neural network, well, you can do it. That's one of the advantages of using the neural network for the physical device models. And there's another thing that I think it is well done is that yeah, it's the symmetry Gummel symmetry test. So that's basically saying that a good semiconductor model, if you develop the semiconductor model correctly, you need to make sure that the derivatives of the drain source current, drain source voltage, and your current the derivative should be symmetric. And so I tried this, like I think the best way to overcome this one, to make sure that your model is symmetric to the VGS, is that you can do something with the data. So if you only train the model with VDS on one side, that you only train the model with VDS larger than 0, the neural network cannot pass this Gummel test. The model is not symmetric. But you can do something that you just flip this current. You just kind of like mirror the current to the other side. Like you have the data when VDS is larger than 0, but to make sure that this model is symmetric to VDS, you can actually mirror the data to the other side. I've tried this. This works. So yeah, but I do want to know if there's any way that we can design the structure to make sure we can do that. Yes, Avi?
The question I have is, okay, so this scale, the physical models are deterministic, right? What I mean is that, they do not involve probabilities in the physics models.
Yeah, I mean that how do they fit into the physics model?
Yeah, my question is because this is probabilistic at the end of the day, right?
Yeah.
How are they to like reconciled?
Yeah, this is something I'm also interested in, but sadly I haven't seen anyone discussing it.
Well, my other question is, because this follows, I think, after Joanne's question, is okay. So this, because we get a some curve after the neural networks do their predictions, right? And
yeah,
how do we? What's the interpretation? Is there like how do like physicists interpret this models? Because they're very
physics
like,
of this neural network model.
they don't like black box phenomena, I'm guessing.
Again, I am trying. I was trying to see if anyone said something about it. I haven't found it, so I decided to work on it myself. I'm working on it. Yeah, I hope I didn't see. There's only one people I think. He had some discussion on it, but not quite. The computer vision. Yeah. I think. Yeah. I agree with that. That's the same thing with the Kuma symmetry test. So I only see one people who trying to solve this. Let me try. Yeah, why didn't I put it there? So there is one people who try to solve this. I think his name is no, not this one. Yeah, where's my side? This is paper. Sorry, I probably lost it. So, what I can say is that there really isn't much discussion on kind of like how physics is incorporated into your network here. I'm working on that. I hope I can present it one day, but yeah, there really is not much discussion. So, okay. But I do want to point out one thing is that like all these models are kind of like all of them use I haven't seen anyone use like real experimental data, and when it comes to experimental data, there's kind of like a lot of things you need to consider. So first, there's some naughty. There's so I tried yeah, so I think that what may be a big advantage of using neural network for semiconductor model is that yeah, it's like for all these models, their input data are from the either BSAM or TCAD. That's kind of like they already built a physical model. But I think it would be more interesting if we can use use experimental data. That's kind of like using something unknown, like building models for something that we do not know. I think that would be more interesting. But when it comes to that, there's some naughty thing in semiconductor called hysteresis. What it means that, like, if when you measure your data, like when you measure it for the first time, you may follow this line. But when you measure it for the second time, it may follow this line. And the third time, it may go to here. So something like that. Well, if you only have like one parameters, it will be easy to model this. But what if on the case that you have like multiple parameters? What if kind of like you only have one line, and yeah, I think this is kind of like a difficult thing is that when we are really dealing with semiconductor devices, we may have kind of like the measurement is not necessarily correct. There are noises in the measurement. There are kind of like circumstances induced, and there are kind of like other things. So, and there could be like and there's also lots of cases that you thought you build the same channel. You thought you build the same channel, but very small difference in your channel is gonna cause a big problem. It's gonna cause a huge difference in your output. How do you model it? I think that is and the question is, how do you model it? So for semiconductor device, this is not like images or voices that it's kind of like a very low cost to get samples. For semiconductor device, it's very kind of like, it's very costly to build and semiconductor devices. So usually you have very few data with a large noise. So, and I haven't seen anyone discussing the physical, how to relate neural network with physical behaviors. Yeah, maybe try. I still didn't see anyone. I'll try to work on it. Yeah. So, but yeah, like if we do have like a good physical explanation of the neural network for it, I think that would be very useful. But so biggest issue, I think, yes, one of the biggest issue is that you don't have like models for is that you don't have a very good explanation of why neural network works on semiconductor device modeling. And the second one is that when you're dealing with the real world, you're gonna have lots of noises, and you end up like you may model one thing well, and it fails on the other parameters. So I've seen how ways to do that. So yeah, I'm preparing my paper. So something. Is Naya?
Yeah. Hey, Sholin, it's me.
Hi.
What were you saying there about, like, were you saying you haven't seen many people use like neural networks for physical systems or something?
I
What were you
was. Oh, sorry.
Go ahead.
I would say I haven't seen a good explanation of why neural network works for semiconductor devices. I don't see much like physically based like models for semiconductor devices in this kind of series, like why some structure work, why some structure will fail, how would the structures of your neural network affects everything. Mostly, I think it's like I think the most advantage I've seen is for basing on your loss function and like how you process your data. But I do think that and how to process your data. So, but frankly speaking, I think the structure matters. And yeah, and but like if you're talking about like using neural network to prop physics world, I haven't seen it in semiconductor field, but I've seen it in other fields like biology and chemistry or geology. Someone did that.
Okay.
Does that answer your question?
Yeah, I was gonna say, because I've seen and I know some packages where people are doing like physics-informed neural networks.
That one, physics informed neural network. They are solving derivative functions.
Yeah, differential equations, stuff like that.
Yeah.
With neural networks. So I didn't know if that was related to what you were saying, but it sounds like on semiconductors.
How to say PIN, the physics informed neural network, that one is mostly on, they're kind of like solving derivative functions or combinations of derivative functions. Okay. But first, I think first issue is their accuracy. People have argued that those physics informed neural network does not perform as well as like other differential equation solving softwares. Yes, there are a lot. There are traditional ways to solve the differential equations, and frankly speaking, I feel that they are more easy to use. Like PIN, like you need to put everything with your coding. Yeah, I don't feel it's very user friendly.
Yeah.
Yeah.
I had one more thought, Sholin. So, like from my background of like physics and stuff, I think of like the ideal gas law, like PV equals nRT, for example, and you're relating. Do you know what I mean?
Mhm,
Yeah. So like pressure, volume, temperature.
mhm.
You set any two of them and get the third one out, right? So you
Yep.
can set pressure and volume and get temperature, or you could set pressure and temperature and get volume. And that kind of reminds me of like what these are doing, right? So like, you know, this compact modeling could be any number of variables, and you need to be able to specify all but one and predict the other one, right?
Mm,
Is that
I
right?
guess. Yes.
Okay, so
But
how,
like,
how does that work with a neural network? Because from what I understand in a neural network, like let's say there's 5 variables,
Mm.
them would be features, one of them would be the target, and you've built a function from these 4 to the 5th.
Mm.
For example, you couldn't then input this as one of the 4 and then predict this one.
Yep.
I mean, so you have to build a new network for each one of those permutations, or how do you do that?
I would say that if you only have PV equals to nRT, what I will do is this kind of like solving, like if you know PV and R and you want to solve T, then you can just build a neural network to minimize the losses that the neural network predicts and your T and the real T. I think that will be easy to. Yeah, I've just started on like reading the probabilistic machine learning paper,
Yeah.
machine learning book. I was hoping that one can help me, but I think that to solve functions, I think there's something that neural network can do. Yeah, it's basically just solving a function. Yeah.
Sholin, if I could jump in, it looked like
Yes.
everything you showed, you were always predicting the current. So it
Yes.
wasn't that sometimes you were predicting something else. So Grant, I don't know if they're ever changing around what they want to solve for. I think
They also they also predict the capacitance, but they build another neural network for that. They
Yeah.
build 2 neural networks, one for current, one for capacitance.
Yeah. So it's not like they're ever trying to predict VDS, I don't think.
That's what VDS.
Like that's always one of your inputs. It's never like what they're trying to predict, I don't think.
I think they tried that.
Okay.
Did they try that? Wait, predict VDS?
Yeah, but the bottom line is you would build a separate network for that. You wouldn't somehow modify the network that's predicting current, right?
Yes, because the current is something we want. VDS is usually like user controlled. You decide what VDS you put in. That's not something we want to predict. That's more like an environment. But like IDS is what you want to get, and what IDS is something that the VDS is that you push a ball. IDS is that you want to know where the ball goes. So usually VDS is something like the environment. That okay?
Yeah, thank you.
We usually don't want to so there are some parameters that we don't want to predict. That's so usually what on the input side is something that is something of the environment. It's not something we want to predict. What we want to predict is obviously IDS. IDS or see the capacitance. So the output of the channel is what we want to predict. So that's that answer your question, Ed.
Yeah.
So my question had to do with you. It sounded to me like you were saying it's very difficult to experimentally build different gates and measure them and collect data that way. That a lot of this data is coming from some kind of simulation software.
Mm,
Is that what you were saying?
yes.
So
The issue is that first, it's very costly to build semiconductor devices. Like if you build one wafer, it could cost you like I don't know, like in laboratory, one wafer may end up costing you like 500 or 1,000. But you do not, but you will not get like lots of but how do you and you only kind of like get like 500, 10,000 devices as most on your one wafer, but that already costs you $10,000. First, it may fail because somewhat that your device just failed and you do not know why. So you may kind of like have to do something again and again. And second thing is that we cannot use experimentally to have all the possible combinations of your semiconductor devices. And that's why we want to have models to tell us like how some of the parameters changes everything. Yep.
Yeah.
Yes.
So my question is, if you're using simulation software to provide the training data, then it sounds like the answer is sort of already known because you have the simulation software that tells you what the answer is.
Yeah.
So is one of the things that people want to do is to train a neural network based on various inputs, from the simulation software, and then extrapolate out to new inputs and see what the neural network would predict for those new inputs that have never been seen before?
Are you saying that we train the neural network with some data set and then compare how the neural network predicts with some data they haven't seen?
Yes, that's how you train and evaluate it. But I'm asking, let's say you train and evaluate it and you think it's working really well. What are they going to do with it? Because if they're just going to predict things similar to what it was trained on, they already know the answer. The simulation software already told you the answer.
How is that kind of like how the neural network can predict the real world? Something like that? Or like how neural network produce knowledges?
No, so like what I'm saying is like classic example, we predict the price of a house, right? So we predict, you say here's 5,000 houses that were sold in the last year. I'll tell you how many bedrooms, how many bathrooms, various inputs, and you predict what the price of the house was. Okay, and where my question lies is that then, of course, when you evaluate it on, let's say, another 500 houses it's never seen. Okay. But the goal of this is that you're going to have it predict the price for houses that are very similar to the houses that it's been trained on. Not identical, but similar. Okay. In its parameters. And so if you had simulation software, you could have just used the simulation software to predict the houses. You wouldn't need a neural network in the first place. Okay.
Yeah, that's true.
One thing that you could do with something like this, though, is you could say, I have now trained you on all of this data of houses in Boston. Okay. And in your training data, the biggest house you ever saw was a 6-bedroom house. But now I want you to predict what the price of this 9-bedroom house would be. So now you're predicting something that's not similar to all the stuff you're trained on. So that's what I would call extrapolation. Okay. And neural networks don't necessarily do well for extrapolation, where you go beyond what you've been trained on. You know what I'm saying? So I'm just trying to figure out, because I don't quite understand what the value of the neural network is if you have simulation software that's going to tell you what the current's going to be anyway.
I don't have.
So
Yes.
Can I? So I think this relates to my earlier question, and my takeaway from it, Ted, was that it's like it's not about predicting for a single gate. It's about, if you can model a gate, then you can model 1,000 of them connected to each other, and running a simulation with the simulator with 1,000 gates is very slow or expensive, but neural networks are fast, and maybe you can simulate those 1,000 gates very fast, something like that. So that's sort of what I got from Shulin's earlier explanation.
Yeah, that's one
Yeah,
point.
I guess I could see how that would be the case, but it seems surprising to me because like if all of my gates have sort of the same construction or whatever, you know, I'm not purposefully building them differently to have different whatever channels length, channel width, whatever. Then when I run the simulation software, Jayanth, like I can just store a table that lists the current predictions for a whole bunch of different inputs, and maybe there's even worst case like 1 million of them. But I mean, 1 megabyte of data that, you know, these days is nothing, right? So I can just have this giant lookup table, and that's extremely fast, just by caching all the different outputs from the simulation software. Does that make sense?
Yeah, that makes sense.
Yeah. So I think, so I think that the simulation software that's out there, at least at a gate level, is super slow. It takes hours sometimes to run a simulation.
That's the case for this one. I think that might be the case for this one. If you kind of like have different combinations of it, it's kind of very hard. You can have like millions of combinations. So, and TCAD, yes, if you run TCAD in this way, it's gonna be very time costly. It could take hours to run just one graph, but you have some.
And so if with neural nets, sorry, go ahead.
No, I was just gonna say it may be slow, but you need to provide enough training examples for your neural net. So you're going to be running a lot of simulations just to give it training data. How much better is it to have that neural net than to just like build a table and cache all the answers from your, you see what I'm saying? Like,
I see what you're saying. Not sure. I think what the author does say that ideally they should use experimental data, and they didn't. And I think what all they try to do is to prove that neural network can be used in semiconductor simulating. But in real world, we do have lots of devices that still do not have a very good model. So the material I have been working on, I have seen models since 2015, yet it only predicts kind of like some parameters in a small region. If that's like, because that's kind of like found mathematically. If you want to elongate to more regions, more parameters, no, you cannot find that.
Yeah, and I mean, looking at the curves on the left that you're showing right now, slide 18, right? That is a very irregular shape with that little pointy bottom, that peak, right? So I can see where it would be valuable to have a neural network that can accurately predict, because that's a very difficult shape curve to predict. The first one you showed wasn't so bad, you know, it was sort of
like this one's.
Yeah, so some of these are very weird shapes, and so I can see like, yes, I really would want something that does a good job. But what I'm wondering is, how would the neural network ever do a good job predicting some of these weird shapes if it didn't have a lot of training data?
No, it can't.
Right?
So far, I think with that structure, they can't.
Yeah, and so then that's sort of the dilemma, because you'd have to run so many simulations to provide all that training data that maybe then it can generalize.
So if I may build on that point that you're saying, Ted, so is this the problem? So I was thinking the same, that the lookup table is what would be an easier way out. But then I'm thinking that, is it highly sensitive to the actual voltage value, to the whatever precision, that you may not have a lookup table for the level of precision that you need for these simulations or for these actual gates? So you may have to rely on the neural network to provide you that value, assuming interpolation may not work as good. And the only place where interpolation may be a big challenge is those weird curves.
I didn't quite
Yeah.
understand.
I have a question actually, if I may. So if you, let's say you model a single transistor very well, now if you want to model 1,000 gates, what do? Do they construct like another network that, you know, interconnects all these individual neural networks, or how do they do it? How do they do the 1,000 gate simulation from neural networks?
If you do have 1,000 gates, so these models, basically you have the same you have the same shape, you have the same material, you have like almost same thing, but you just kind of like have, let's say one have kind of like but one may be a 10-meter long channel, one may be an 8-meter long channel. They have multiple data like this. So as long as your material, as your shape is not changing, well, you can just use one neural network to produce all the channels that looks the same, that kind of like with the same shape and material. It's yeah. So like if you have 1,000 1,000 channels, that's basically you have thousands combinations of inputs. You just put all of them into a one well-trained model, and you get all the information you want. Does that answer what you
I mean, like the circuit you were showing earlier, right? So if you take something like that, let's say you have a model for each gate.
Yes.
And now you want to model the whole system.
Yeah,
how do they incorporate the neural networks? Do they build another one composed of smaller ones, or what do they do?
That hasn't been invented. But I think that would be a good idea. But how to say, physically, so the current physics model will probably build another neural network for this one. But I think there should be a way to kind of like use one neural network that's kind of like use combinations of different neural networks to achieve this one. I think this is physically possible. Yeah, that needs working.
Is that where they're headed? I'm sorry, I haven't read the papers, but like, is that what is that sort of, you know, where do they think they're going with?
I don't think they have much discussion about it. So they do try to show that yes, with the prediction, with the model, you can predict the behavior of the circuit. So yeah, this is their performance on the circuit. Let me see how they do their gauge.
So yeah, so I was wondering if you do one sort of construct a larger neural network by composing many of these small ones, and the inference on that larger network would be much faster than running the simulation. This was how I was imagining. That's right.
So if I can throw in a comment, so that diagram of the oscillator,
yes.
it shows the actuals in black and the neural network in the dashed red. So
yeah.
So what's happening there is it's not making a single prediction, but rather what's happening is its inputs are changing over time, and the neural network is making predictions for each time step. So I think one way in which maybe they use this neural network is to say, what's going to happen as my inputs change? As opposed to what you're saying, Jayanth, which is what if I connect together 10, 100, 1,000 different gates together? Because you could just make 1,000 copies of your neural network and just connect the right output to the right input and do that. But it looks like in this case they were, measuring it over time as opposed to instantaneously just doing 1 point prediction for a collection of gates.
Right. Yeah. So I mean, I think there's two things here, right? One is that ultimately I was imagining that they want to simulate at a larger circuit level with many gates. And when you're simulating that, the simulation involves some input waveform, you know. So that's over time, you need to be able to predict or simulate how the output changes as you change some input way out there or many inputs. Because it's just, for a larger circuit, it's just not VGS and VDS, it could be many other things.
Yes.
So that's sort of, but yeah, so I think there's a time component, but also I was wondering if there's like a larger circuit component, because just doing it on a single gate, I don't know if that's their end goal.
So I think currently there is these are kind of like in two systems. There's system for the device modeling of the device, and there's also system for the modeling of the whole system. But so far, I haven't seen them combined. Yes. So traditionally, what we do with the circuit is that yeah. Traditionally, what we do with the circuit is that if we know these parameters, like the derivative GM, and also some of the capacitance, we can use these parameters as inputs to for circuits and try to kind of like matching everything. Yeah, that's kind of like the system level. So, but yes, there are always. So what the system does is that we know the model, and we just kind of like try to basically have a separate system to do that. But I haven't seen anyone that's kind of like they use because this one like in this paper they just have one line talking about that figure, that's figure 8, saying that we just like by hard coding the weight, bias, and metric multiplications into Verilog A. I don't know Verilog A, but I think if they just have one word of saying that, from my understanding of how amplifiers how the oscillators are modeled, they probably incorporate they probably incorporate the calculated GM, which is the derivative, and some of the, so usually kind of like the oscillator is that, okay, we know the VGS is at some point, we'll calculate the derivative, which is GM there, and we incorporate that number into another set of the function by the system and calculate everything else. So it doesn't necessarily have to use the model. It doesn't have necessarily to use the model to use the whole model of it. You just need to get one parameter from your model. So that's how the system works. And so I haven't seen anyone like using like the whole transistor model into the system buildup, but I think it was well because they are essentially built together, and the building process is going to like interfere with each other. So I haven't seen the model, but I think it was well to kind of like if you have a whole system, if I have a kind of like this is the neural network 1, this is the whole system is the neural network 2. I think if you can do that, I think it works well. Yeah, is that okay? To me, I think nice. Yeah. Sorry. Yeah, I haven't discussed the neural evolution one, but still cannot stand it. So, any questions?
So going back to the question that Ted raised, if we are looking at a single transistor modeling, I mean, I imagine it can still be useful if the number of parameters that are going into the circuit explode. then the lookup table can be a very big one to well, I don't know, it depends on the performance of the GPU for the kind of neural network you have, but I can imagine that there may be scenarios where it is better to have a model than a humongous, like, table. But other than that, the only other reason I can think of is the interpolation limitations, especially around the kinks and the turns, and when like U-turns.
Yeah. I think like it will be exciting if we can have models that like we don't have the simulation software for that, and we do not have a very good physical model to explain everything, but we can still model it. I think that would be great. Yeah, but that's challenging because
So so in A in the middle there, it says it has 1, 2, 3, 4, 5 parameters. Is that what it is? The length, width, thickness,
like this
spacer
one?
thickness. Yeah.
Yeah.
Are these just the parameter for the? Yeah, these are the parameters that we're modeling along with the voltages, right? So there are 7 parameters that go into the circuit.
For this one, no, but for this one, yes. They goes in with it. So they all kind of like they're all here in the inputs. So this is kind of like how how the shape of your channel is. So so that's for the like 1000 devices one. So because all these parameters are already in your inputs, so if you do not change the structure of your channel, you can kind of like model like channels with like a different length, different widths, and different thickness of the gates and things like that. So that only needs
Right,
one neural network.
Which is coming from your mask for your chip, right? So from there, you know exactly how each of the gates capacities are.
Yeah, like basically, if you know the shape, that's kind of like, yeah, that's if you know the shape, you can model everything.
Right, and then you had this other picture where you had those yellow and black kind of, like you said, it's a very complicated, bigger circuit, and that's where it could. I think it was in the paper.
This one's?
No, in a paper. You had a paper.
This one?
In one of the. Yeah, on the right side there, right? So I imagine, yeah, oh no, it was right there. Yeah, on the top right, out of plane polarization extraction methods from the phase angle. Yeah. So I imagine that there are multiple gates there, and the exact parameters for each of the gates are determined based on its exact location where it is. Is that what it is?
No, this is not a gate. This is kind of like you have different rocks and grasses in your channel. So a gate is not kind of like something very smooth. It may for this material, you kind of like have like a, let's say like you have a water channel, you have randomly have rocks, grasses here, there, and you have net somewhere, some fish net somewhere. All of them will affect your characteristic because they create some kind of frictions. So what they are trying to see is, and this is, yeah, if you have something like this, you have randomly distributed stones and the grasses. Sorry that my cat is trying to disturb this. He's trying to get my attention. Mr. Q.
Yeah, so basically you're talking about microscopic differences, non-uniformity in your semiconductor.
Yes.
When you build the gate.
Yep, and this is very hard to model. And that like it's very hard to build a physical model, but it's possible to have a neural network model because this is like just statistics.
Yeah, so this is where I can imagine where you throw in some, I don't know, more and more parameters, and may help you against trying to, just look at look back to or look into the lookup table to get your response.
Yeah, as the number of parameters grows, this lookup would just be ridiculously too big. Yeah, that makes sense. All right,
that's-
well, Sholin, I apologize, but we're running out of time.
Okay.
So is there anything else that you would like to just sort of close with? Any final comments?
Final comments, I think it would be great to use experimental data, but it's hard. And I also, yeah, I really agree that like if we can have like combine this small model with something else, that would be great. I think that's what's really needed is that like if we have a physically based model. Because like mostly for development of semiconductor devices, you're gonna see tons of device structures with very little data. Yeah.
Awesome.
So I hope we can see one day. So
Great. Thank you. Thanks so much for sharing with us all the research, and it's clear you did a lot of reading and looked at a lot of different papers and things. So appreciate you doing all that and then sharing with us what you're learning.
I hope this is of some interest. Like I said, this is not a very good developed field. So
Yeah, no, it's always great to see applications, like how are people actually using machine learning? How are they actually using new neural networks to try to solve different problems? So it's really nice to see, you know, a real use case.